Um, a very good evening to everyone, and thank you for joining us today. I hope to see more people as this session progresses. A quick introduction. My name is Aishwarya, and this is the fourth day of the series on realistic approaches to bioprinting, wherein we have a few guest speakers on board who would give us their research experiences in general. Yesterday was a talk given by Dr. Shreya Malhotra from IIT Kanpur, who had given us a very wonderful session upon the whole processes in terms of cardiac tissue engineering, organ on a chip printing, etc. In case you've missed that, you can easily find the link on YouTube as well as on LinkedIn. Please find time to watch that. I hope you continue watching this. And towards the end of it, I will also introduce the next speaker for tomorrow. So until then, I will go to presenting my screen and I'll start the session. Hello everyone again. So today's topic is going to be biomaterials development in 3D printing applications. Again, my name is Aishwarya Shirur, and my role is as a technical specialist at Altum Technologies. And Again, a quick introduction of our company. We are a 3D innovation platform company. We have Dassault Systems, MSC Software, Statusys Solutions, Artec 3D, BioVia Solutions, as well as selling solutions on board, especially the 3D bioprinters. And we are, quite a recognized company, and we also have been recognized as platinum partners by few of our partners on board. And Talking about our customers, like I've already said this before, we have a large set of, hold on people from different areas, different solutions, different industries, and we hope to keep growing that manner. Um, Coming down to the topic and what we spoke, um, we had initially spoken about what bioprinting was, what tissue engineering as a concept is, how tissue engineering concept has been added into the area of 3D bioprinting. And following that, we also have today's topic, which is on the biomaterial part. And yesterday we had a specific application, that is cardiac tissue printing. So, in general, when you talk about the challenges that exist in the healthcare and life science realm, it is going to be the lack of organ transplants. We have waste due to wrong testing methods, and then also we have lab to shelf time. These three being the main challenges in general are reasons why 3D bioprinting has emerged as a solution, as a technique that is a possible technique towards eradicating or even minimizing the effects of these challenges that we have. So, coming to the main topic, we I have given you briefs of what tissue engineering is. I've given you briefs of the details of what a 3D bioprinter is. So the main unit, or one of the adding units over there, is going to be the material that we are going to use in terms of printing any sort of structure. A biomaterial basically is designed in such a way that it is biologically available. It is something that can easily interact with living systems, and over a course of time it would help in therapeutic as well as in diagnostic procedures. The idea behind biomaterials are biocompatibility. So, biocompatibility is basically the ability of a material to perform with appropriate host response in a specific application. The idea of keeping a cell type or a living body intact or in contact with a biomaterial is what biocompatibility generally stands for. And I've also mentioned about these general materials in the past, where you have PEEK, you have PCL, and you have many other materials which, or any general polymers as well as metals which have been used. And we are now stepping to a different direction which aids these common issues that we have. That is, whenever the challenges exist with conventional methods, we will have tissue engineering methods being put forward. So, Again, a quick intro on what tissue engineering is. It's an interdisciplinary field which applies the principles of engineering, life sciences, and the whole idea is development of biological substitutes in order to restore, maintain, improve tissue functions. So, when we talk about this, we have scaffolds, we have chemical and physical factors, and then cell type. So, in the scaffolds, we have porosity, cyto tissue compatibility, bioactivity, cell attachment and migration, and mechanical properties. And the cells, on the other hand, are the type of cell we have taken, the relevance of the model, the interaction that exists, the signal pathway, and the integration of flow. Um, so, having and keeping all of this in mind, I will be talking of what the materials are. Now, these materials or these biomaterials would be available in several forms and maybe injectable, maybe they have a specific mechanical and biophysical property, they would have release of biomolecule, they would have a specific degradation kinetics, and there eventually, when there is a degradation, there should be a lack of toxicity. Architecture, morphology, and delivery in case of biomolecules is also one of its functions when it comes to the biomaterial that is used. So, whatever biomaterials that are used will eventually form an architecture along with giving you the biomolecules, and this will stimulate the niche cells. That is, regeneration is eventually brought in when when these materials along with cells are put together. So, when you're looking at tissue engineered materials, you are looking at the strength of the material, elasticity, biostability, lack of toxicity, magnetic properties, host response, mechanical stimulation, a correlation between biocompatibility and bioavailability, just give me a second. There's a small glitch. So I've mentioned on these topics about strength, elasticity, biostability, lack of toxicity, magnetic properties, host response, mechanical stimulation, a correlation between biocompatibility as well as printability. So, spatio-temporal arrangement of the material is also quite crucial. And then we have the main concept. So when you're using biomaterials, there are several types of biomaterials, and they're in their crude form. So when you say they are in their crude form, they are ideally present at a state where, just a second, I'll just make sure everyone can hear me. Yeah, I believe everyone can hear me. So, yeah. So whenever the materials are present, they are present in their crude forms and they're supposed to be processed. So when it is raw or when it is in its absolute crude form, it's not very effective or it's not very efficient, and often it happens that a lot of other components which is present along with its raw material. Say whenever you want specific component from a source, there's always a process of processing it coming down to just that material, right? So that's where you would have to extract something in one particular form and convert it into another form. So here we are using hydrogels, and the main essence of bioprinting is the use of hydrogel material. By definition, a hydrogel is a three-dimensional network of hydrophilic polymers that can swell in water and hold a large amount of water while maintaining the structure due to chemical or any sort of physical cross-linking of individual polymer chains. Now, hydrogels undergo a significant volume phase transition or uh, gel sol phase transition in response to certain physical or chemical stimuli. So, usually, hydrogels have the capability of attracting water, basically absorbing quite a lot of water. It swells quite a lot and it can hold also a large amount of water, while it is also maintaining the physical as well as chemical constituents which are present. So, when you talk about any type of material, any type of polymer, the importance of the polymer is how the chains are. That's why you have um, polymerization, or you hear of words like polymerized chain reaction. So, basically, these bonds which are present between the materials are in such a way that they are easily manipulated through chemical or physical stimuli, and these stimuli in turn help in giving you the kind of structure you want. Now, the physical stimuli would include temperature, electrical and magnetic fields, solvent composition, light intensity, and pressure. So, the chemical or biochemical stimuli would include pH, ions, specific chemical composition. So, when you talk about these materials, hydrogels are quite unique because they are very good in aiding healing, or aiding the cells which are within the constituents. And while it's also giving you the structural integrity, it's also something that can be easily processed, easily manipulated, and eventually it helps in trying to print the structure that you want. So hydrogels are in the form of polymers, or they have a specific concentration, they have a specific molecular weight, and also chemical composition. So, when you talk about hydrogels, you will keep in mind few factors which are very important. So, this is a factor which is written by Malda, and these are standards which are followed by almost every researcher in the field, saying, okay, this is the kind of correlation we need to consider when we are working with hydrogels. So, one being gelation. So gelation is basically giving it a fixed shape, right? So it provides a shape fixation. Next is a timing of gelation. Other factors being physical and chemical as well as cytocompatibility. Now you have viscosity, which is how the viscosity would contribute. Now all of these factors like viscosity, the nozzle gauge, the shear stress, the fabrication time, all of these have a direct correlation to the printing fidelity, that is how well is the printing happening, as well as what is the viability of the cells. Basically, if you're printing with cells, will there be better proliferation, will there be good differentiation, is there any amount of tissue formation. In terms of fidelity, you have construct size, the resolution, the shape stability, all of these factors, all of them put together, that is, if you have any effect of shear stress causing while printing, then it is automatic that if there is too much stress, then possibly the printing will not be too well, the construct will not come out too well, but also your cells will not be too viable. So there's a direct correlation when you're considering these points. So I'll go one by one with all of these factors that contribute to it. So requirements being printing fidelity, the first point. So here you require high printing resolution when you are trying to print any structure. There should be an ability to give you a good construct while you're printing. There should be good fabrication speed, shape stability, and post printing processes. So if I have to print a structure of specific fidelity, there should also be a case where um, you have the stability within the structure, that once you remove it out from the site of printing, it also stays in its actual form. So that becomes an important point about shape fidelity. And for shape fidelity, you have factors of the materials that are essential. One being viscosity. So viscosity basically influences the printing resolution, and also it also has a direct impact on thixotrophy. Thixotrophy is basically the dependence of a material over time, over stress, and how it retains its shape, it retains its conditions even before applying a shear stress over it or after it has been printed. So what could be the influences towards printing is one, viscosity, second being shear thinning behavior. Shear thinning behavior is basically the viscosity decreases the moment the shear stress is increased. So now this factor, you have to play around with these factors to ensure better amount of printing, better amount of reproducibility. If I know that the amount of shear stress that a material can bear is only so much, or this is the right amount of shear stress, then I can keep that in mind and design the next batch of materials for printing in that manner. Next is gelation. So gelation is, like I said, it depends on transition temperature, the gelation temperature, or the presence of materials, presence of physical factors that will eventually lead to cross-linking of the material or polymerization of the material. So at specific conditions, fluid bioinks transform into a gel with a much higher viscosity. So if you have high temperature, possibility are that the viscosity will lower as the time progresses. So selecting the right temperature of printing or selecting the right pressure of printing becomes important. Now the stability over time is another factor. The change of mechanical properties over wholesale, basically the conditions of temperature while you're printing also play a very important role. Cytocompatibility. So cytocompatibility means how cells can be compatible. How is the viability of cells? When you're talking about biocompatibility, it becomes a very larger picture. Cytocompatibility is basically how a cell reacts at a specific site. Optimal conditions for desired cellular processes are stiffness, the mesh size, the bioactive additives which are added. So you have sterility, which plays a very important role when it comes to cytocompatibility. You have to ensure that there should not be any contamination, maybe of bacteria, of fungi, of yeast. You have a specific tonicity. You have say isotonic solutions, so there should be a stable osmosis within that site. There should not be excessive of salts or any other material that could penetrate to your through your cells, disrupt your cells, cause any sort of deformities caused related to the levels of solvent salt solutions at that site. Next comes pH. pH is that you have to maintain uh, a specific pH. So if you go above 7.4, this would cause cell cytoplasm contraction, and a pH below 6.5, which is acidic, can stop cell activity. So you have to maintain a specific pH, that is a neutral pH or something between 6.5 and 7.4. Endotoxin levels. So material when being processed has to always be tested for the endotoxin levels, and there is a percentage, or there is an angle, there is a number above which you cannot have it, because if then you will not consider it as a standardized or a quality product or a quality biomaterial when it comes to printing with cells or printing a specific format of structure. um, so cytotoxicity again being, uh, there is effect on the cell viability and how it would also affect the printing parameters. So bioinks, hydrogels are constituents of bioinks. These hydrogels are smart structures. They are hydrogels plus etc number of materials put together, and the name bioink is actually given specific because we need to use some sort of ink to do the printing process, and this is specific to the additive manufacturing space. So what makes a bioink is the first question. Bioink is basically constituent of the main polymeric component, say the hydrogel material or any synthetic or artificial biomaterial or a polymer. Then you have thickeners, you have complementary components and bioactive components. Going down one by one. Main polymeric component, let's assume gelatin, or alginate or chitosan or collagen. These are general polymers which are in the processed form, in the hydrogel form. To that you have thickeners. Now if there is a problem with the viscosity or the stability of your material, you would require adding an additional material to it which can help in controlling the mechanical properties of the material, especially the viscosity, the printability of the material, and will allow in creating stability. Then you have complementary components. Complementary components would be buffers. You would have maybe cross-linking agents, which will allow in solidification of the material. You will allow use of materials that can allow better cell attachment, say maybe RGB, RGD structures, or you will have buffers. You require something that can be a thinner as well to the solution. You want something as a stabilizing agent. All of these are complementary components. Next is the bioactive components. Bioactive components will be the cell suspension media. It will be again the cell type which is used within it. It'll also be the type of components that will aid in terms of using that material. Then you have considerations when developing bioink for 3D bioprinting tissue. Choice of material. One thing is the material should be easy to print, but even if the material might be the easiest to print in terms of a lot of shear, a lot of pressure applied while printing, there are possibilities that the cells might not sustain. So you have to create a good balance between shape fidelity as well as the cell viability, which is the main idea of bioprinting of hydrogels or any biocompatible material. Then comes the cell type selection. So when you're selecting the cell type, it has to be specific to what function you want to produce. And if these functions are not met, or the cell which is used is not compatible with the material you're using, then there is no point of um, using a cell type at all. Next is the method of printing. Method of printing would be the technology you would adopt when it comes to printing with cells. So method of printing would include, like I said before, extrusion based printing or inkjet based printing. We have the EMD system for that. Then we have DLP based printing, syringe pump printing. That is a method of printing. Next is the tissue structure. Tissue structure would be what is the model that you want to print with, what is the geometry of it. Incorporation of growth and differential factors, capability, that is cross linking intensity, etc., pattern or infill. So chemicals and and cells. So pattern or infill is actually a very broad concept, but when you talk of it, patterns or infill are good in terms of allowing better stability of the structure. Every structure has a specific geometrical stability which can allow whatever you print to have better amount of structure in terms of fidelity, in terms of holding the whole printed part together, or even saving material or giving equal amount of mechanical distribution among its crevices, its edges, its perimeters. So we have some common names. We have honeycomb, we have grid, we have rectilinear, we have triangular. We have many such standard structures, and there's also percentage among them. You can have 5% infill, 10% infill. Basically that is how much of your material is actually required in order to create the design you want, and how much is it impacting the mechanical stability of that, also keeping in mind that you have the optimum amount of material to be used. Sometimes it's not necessary to use too much material, because if you're using too much material and trying to fill the whole structure, there is also direct impact on the porosity that is being required when it comes to creating a scaffold. So, like I mentioned before, we have natural polymers and we have synthetic polymers. So natural polymers would eventually have better biocompatibility, low toxicity, cell mediated proteolysis, degradation, which is degradation is controlled, or in fact a higher amount of degradation. You can work around with the viscosity with the help of the molecular weight selection. The ionic cross linking would be the mechanical stability or post printing. Examples are fibrin, collagen, gelatin, chitosan, etc. And then you have synthetic materials. Synthetic materials are basically controlled mechanical properties, easily processable, easy modification of materials, and examples are PLA, PLGA, etc. Then, okay, example of alginate. So this is an example of creating maybe a microfluidic device or trying to print to create alginate micro arrays or alginate beads. So when you're trying to create micro arrays or basically organoids, this is where they have used syringe based printing, or they have used EMD based printing to create droplets. We also have chitosan. Chitosan being a material derived from shell crustaceans. These materials also have some good features in terms of allowing tunability. Uh, Although they have low viscosity, but they also are very compatible. Beyond a certain percentage of the material can cause toxicity, but using the ideal amount will also aid in terms of um, antimicrobial studies, in terms of cell toxicity and other factors. So thickeners I mentioned. Um, so example, shear thinning, temperature stable materials are what thickeners are, and they eventually increase the viscosity and improve the printability. Nanofibrillar cellulose is one example. So initially, when they tried to print with alginate as a material, there was a lot of shear thinning happening. There was no stability, no good shape fidelity, and in order to allow better printing, or to get a better structure, what you see here on the spatula is a better structure that was achieved when they added nanofibrillar cellulose to it. Then we have xanthan gum. So here they've printed gelma material, yeah, basically it was gelma material at a very low concentration, with a certain type of cell type, and now again it was added with maybe 1%, 2%, or 3% of xanthan gum. You see there that there is so much fidelity improvement. There was better printability when they used xanthan gum, and also xanthan gum is good in terms of improving the storage modulus. Another material is glucomannan. So glucomannan is basically another material which aids in printing. Here they have combined this with chitosan to improve the printing. So having a direct impact on the shear, on the viscosity as well as the shear rate. Um, Then comes the bioprintability. So bioprintability becomes one point where you have shape fidelity, as well as the concentration of the material, as well as the impact of this on the cell culture or the cell printing which takes part. So you will see that if you're trying to have the best amount of shape fidelity, then you might also not have the best amount of cell viability. If the material is too stiff, then it cannot print at all. But if the material has the optimum stage, then you can get good amount of cell culture. So when you're assessing the bioink printability, you have initial screening where you would check for maybe a droplet or a filament or a fiber formation. You'll also try to see if you're printing many layers together, how will it hold it. That becomes a very important point in terms of initial screening of printability. The next point comes down to the rheological factors. So rheological evaluation would be flow initiation, shear thinning studies, post printing recovery. So, when you are looking at points like viscosity regulation when it comes to rheological evaluations or printing, you will consider the printing parameters. That is the temperature and the shear rate. You will play around with the temperature for certain materials who are sensitive in material. Also the shear rate. What you're saying shear rate is basically the amount of pressure you have applied when you are printing something, and how that pressure has impacted the positioning of the materials within that given cartridge. So the piston would have some amount of shearing on the material, and also the nozzle which you're using will have a clear impact. So using the right amount of nozzle dimension will play a good role in terms of improving both the fidelity as well as the cell type which is used. Then you have polymer characterization. Concentration and molecular weight are two things that are playing a role. So in terms of polymer characterization, you have concentration and molecular weight. Then you have additives, which are thickeners, right, which have all a direct impact on the viscosity. Shear thinning effect is basically the reorganization of the polymer chains. There is a decrease of higher shear viscosity at higher shear rates. You have post printing recovery and stability of the construct. So the viscosity increase post printing. So there is influence. Um, One second. Yeah. So the viscosity increase, or the amount of viscosity, will definitely impact the printing resolution. Then comes the printability, that is extrudability or cell viability. Extrudability basically is how it is, how the pressure has been impacted on the material and how it is coming out of the nozzle head, and how well it is giving me the structure I want to create. Then comes cross-linking. Cross-linking is again a post-printing process, or the impact of a specific material on what you have done. So when you're doing a printing, you have to keep in mind that you have to have the shape of that structure being created. So you have physical methods as well as chemical methods, that is through cross-linking, which can make sure or ensure that these shapes are retained. Physical methods would would be good in terms of excellent biocompatibility. Physical methods, that is if you have a good amount of pressure being added when you're printing it, or light which is being added, then there are chances that you can reverse it. Say if I have used a material, put some amount of material, it has gone through some physical changes, I can also reverse it back to its original state, which can avoid wastage of materials. Then use of additional agents. Then you have maybe softer constructs, or slower cross linking. These are few things that might be disadvantage in terms of using the physical methods. Then you have chemical methods. So chemical methods will provide higher mechanical stability, wider stiffness, but there might be some amount of effect in terms of the cell viability or the biocompatibility. And this is a more sensitive method. So the production of chemical cross-linking methods are very different when you're comparing it to just creating any bioink and printing it with physical methods. So coming down to what Cellink has, what we provide, we have multiple ranges of bioinks or materials. Um, so you can eventually make your own bioink, that is with raw materials that we can provide. You would have basically the concentrated components. Um, then you would have also, we have standardized products. So these products are definitely cheaper when comparative to the standard places that you buy your materials from, in terms of the 3D bioprinting standards. um, there's also you can, you would have a standard process in terms of getting these components. So when you talk about using the concentrated components, you also have solution stocks, or stock solutions, that is concentrated forms of that same raw material in a easily blendable manner. Then you have standard bioinks. So we have a lot of standard bioinks which are meant by names, say example Kaito ink, Cellink bioink, or Gelexa, Gelma material, which is a bioink form. These are ready to use forms because they have been modified and standardized and optimized in a way that you can easily print something out of it. You don't have to optimize it in your own manner. It's just a ready to use printing material. So we have charts which can help you understand with what type of material, what type of cell type this is best efficient with. Then we also have advanced bioinks, which is tissue specific biomaterials, and we have exemplar case studies which can back you up when you are trying to do your project on trying to create a tissue model. Um, then we have tissue engineering kits also, which can aid in the all over process, starting from mixing the materials together, a specific set of protocol, printing the material, having a protocol of printing, and then also doing the stainings or doing the analysis or testing of the material. So this is the kind of things we provide. And the reason I've also included this step because you'll see that how biomaterial development plays a very important role in collaboration with having the right type of bio printer with you that can give you the type of material that you want eventually for your application. So there is a very close correlation in the bioink development sector when it comes to doing bioprinting, and we have quite some experts in the field who are well versed in just doing the bioink development, maybe general, maybe it be for bioprinting. And like I mentioned, we have the most widely used type of printers: extrusion based printers, digital light processing printers. A quick glimpse just for you to understand in case you've missed what extrusion printing is. Then we have the DLP processing. Now, what you see here are two types of printing processes, and you'll also notice that the way the materials are or how they look post processing or pre processing are very different from each other. So, when you're trying to do extrusion based printing, there is a specific type or specific protocol of creating hydrogel extrusion paste inks, and there is also a specific type of protocol for DLP based prints. Here in extrusion based printing, you have the option whether you want temperature to be the cross linking agent, or you want light to be the cross linking agent, or you have any other physical factors to contribute towards the cross linking. But when it comes to DLP based printing, then it is purely a light based printing. It's light assisted. So here the cross linking is happening with light. So you need to set protocols and create materials that follow the process of photopolymerization. So having photopolymerization involved will eventually lead to creating the type of material you want for a DLP based process of bioprinting. So there has always been a lot of work done towards extrusion printing materials, but very limited work in terms of digital light processing based materials, because there is a role or a correlation between the amount of light intensity, the material polymerization, as well as the cell viability. So these three factors have to play around when you're trying to print any sort or any form of material. So this is one example. Um, Here, this is a targeted rheological bioing development guideline, um, giving a systematic correlation between the printing and how different factors contribute to the behavior of printing. So, bioprinting process is strongly influenced by temperature profile, shear forces, and these two play a very important force when it comes to printing in general. Gelling mechanism, mechanical stability, cell adhesion, and printability are also factors. This is basically an example of sodium alginate, carboxyl methyl cellulose, and gelatin. So these are three different materials put together trying to form a stable structure. And this is also comparison between printing them individually. Um, you have hydrogel characterizations which are important when it comes to creating the right amount of printing material, checking for homogeneity, checking for density, rheology, and many other studies that come under it. In the printing process, you have to check the temperature sweep, the processing time, the dependency of the nozzle, and the gelation kinetics. Here, cross-linking studies, thermostability is also something that are important to be considered when you have done printing with certain type of materials. So this is our this is our other solution, which is the BioVia solution, which is mainly for biological modeling and simulation. And yes, so just a second. So yeah, I also wanted to mention about our existing products. We have the Incredible system, basically Incredible series. We have the BioX series. We have the Bio MDX series, Lumen X Plus, as well as the Quantum BioX, Quantum Bio series, basically for microfabrication studies. So I've mentioned of BioVia solution, and interesting factor that we have a guest speaker tomorrow, which is Dr. Kaushik Chatterjee, who would be joining us tomorrow, giving us his insights, his details of how he has used these materials for several types of materials, how he's developed materials, how he's created bioinks, both in the general polymers in terms of 3D bioprinting materials, bioinks, DLP based materials as well. So thank you so much, and please join us tomorrow. Just a second. So if there are any questions, I'm ready to take them. Yes. Yeah. So I'm sorry. I think I can re-answer this question for you. How bioprinting is used in sterilization technique. Um, I'm not sure of what you're trying to mean from this question, but what I would like to say is that when you're doing the bioprinting process, you have to keep sure that there is aseptic environment. The biomaterial that is being created does not have any sense of contamination in terms of bacteria, endotoxins, or fungus. The whole process should be in a GLP, or basically a good lab practice, as well as a clean chamber if possible. Laminar flow chamber is very important when you're trying to do the bioprinting process or creation of the material. Then this was also another question you asked. So the types of buffers that are used are called as reconstitution agents. We use PBS, HPBS. Um, we use sometimes just distilled water. We would sometimes even end up using some amount of materials like NaCl or some buffer salt solutions to work in this process of printing. So I hope this answers your question. I don't see any more questions for now. So thank you so much. I hope everyone has had a good understanding of the concept, and kindly join us tomorrow for our session with Dr. Kaushik Chatterjee. Kindly follow us on LinkedIn as well as YouTube and every other platforms. And I hope to see you soon.